This particular section of the lesson will deal with the aeroplane's speed, including maximum speed, minimum speed, and the relationship between the various expressions of speed such as indicated airspeed, calibrated airspeed, true airspeed, true ground speed, and Mach number. Firstly, let us examine what we mean by an aeroplane's maximum speed. You will have learnt from earlier lessons that an aeroplane will remain at a constant speed when the forward and rearward forces are balanced, as shown here. In this case, thrust is equal to drag. In order for the aeroplane to accelerate, thrust must exceed drag. This can be achieved by the pilot opening the throttle further to increase power. With thrust greater than drag, the airplane will accelerate. As the airplane accelerates, drag will increase. When drag reaches a value which is the same as the thrust, then acceleration will cease and the airplane will have achieved balanced flight once more, but now at a higher speed. Therefore, the highest level flight speed that can be flown by the airplane will be at a speed where thrust is maximum and drag is maximum. Shown on screen are the thrust and drag curves for a typical jet airplane. Let us look again at what we have just learnt, but this time using the graphs. Here, thrust is more than drag, and therefore in level flight, the airplane will accelerate. As we explained, drag will increase as speed increases until thrust and drag are again equal. This speed is the fastest speed the airplane can achieve in level flight. Look at the graph again and notice that there is another point on the curves where thrust and drag are equal. This speed represents the slowest speed that can be maintained at a given thrust setting, since thrust and drag are equal. In level flight, it would be impossible to fly any slower at this thrust setting, since the rearward force of drag would exceed the force of thrust. The area to the left-hand side of the bottom of the drag curve is commonly referred to as the back of the drag curve, or the speed region of reversed command. Flying at these speeds is inefficient and not recommended since a lot of thrust is needed to maintain a fairly slow speed. Notice that at high altitude, the thrust produced by the engine decreases. Looking at the graph now, it is clear to see that at high altitude, the maximum achievable level flight speed is slower, and the minimum achievable level flight speed is faster than at lower altitudes. Thus the range of speeds for the airplane is narrower. This next part of the lesson will focus on the explanation of the various expressions of aeroplane speed. Different expressions of aeroplane speed are used for different purposes depending on whether we are concerned with aerodynamics, operations, navigation, or even performance. In most cases, aeroplane speed is measured using certain types of probes, called the total pressure and static pressure probes, as shown here. These probes help us to isolate dynamic pressure on which indicated airspeed is based. You can feel total pressure by simply putting your arm out of the window of a moving car. However, total pressure probes, sometimes called pitot probes, and static probes suffer from errors. Without any correction to the errors, the speed which is obtained from the probes when dynamic pressure is being sensed is called the indicated airspeed, abbreviated to IAS. Indicated airspeed is the speed that is displayed on the airspeed indicator. If the pressure probes are corrected for instrument and position errors, the speed is called calibrated airspeed, abbreviated to CAS. This speed is also known as rectified airspeed, or RAS, but this expression will not be used on this CD. Calibrated airspeed is more accurate than indicated airspeed. In large, modern commercial airplanes, the air data computer automatically corrects the pressure probe data for these errors and displays the calibrated airspeed in the airspeed indicator rather than the indicated airspeed. The final correction to make to the information received from the pressure probes is the correction to compensate for the effect of compressibility. Typically, at speeds beyond 220 knots, the air ahead of the airplane does not move out of the way. As a result, the air starts to build up and compress in front of the airplane. This buildup of air has an effect called the compressibility effect. If the probes are corrected for the compressibility error, as well as position and instrument errors, the speed obtained is called equivalent airspeed, abbreviated to EAS. Equivalent airspeed is the most accurate of the speeds which are obtained from dynamic pressure. For the most part, this performance CD will assume that indicated airspeed, calibrated airspeed, and equivalent airspeed are the same. The next speed to consider is true airspeed, abbreviated to TAS. True airspeed is the equivalent airspeed corrected for density error, and as the name suggests, is the true speed of the aircraft relative to the air through which the aeroplane is flying. On screen is a very simplified formula showing that true airspeed is proportional to the equivalent airspeed and inversely proportional to the density. If, for a constant equivalent airspeed, the density were to fall, the true airspeed would increase. This means that with increasing altitude at a constant equivalent airspeed, true airspeed increases, as shown by this graph. True airspeed can be calculated by using the tables in the aeroplane flight manual, using a flight navigation computer, or even using the airspeed indicator. True airspeed is mainly used for navigation and flight planning purposes. The next speed to consider is the true ground speed, abbreviated to TGS or just GS. This represents the aeroplane's speed within a fixed ground reference system. Put more simply, it is the aeroplane's velocity over the ground. The true ground speed is equal to the true airspeed plus the wind component. If there is a tailwind, then the aeroplane's speed over the ground will increase by a value equal to the speed of the tailwind. So, in our example, if the true airspeed is 250 knots and the tailwind is 20 knots, the true ground speed is 270 knots. Conversely, if there is a headwind, the aircraft's speed over the ground will be reduced by a value equal to the speed of the headwind. So, in our example, if the true airspeed is 250 knots and the headwind is 30 knots, the true ground speed is 220 knots. If the headwind or tailwind components are not already known, these can be worked out using a flight navigation computer or by using the supplied CAP 698 manual on page 49, as illustrated here. At speeds higher than about 220 knots, some of the energy of the aeroplane goes into compressing the air ahead of the airplane and locally increasing the density of the air. Compressibility affects the amount of drag force on the aeroplane, and the effect becomes more important as speed increases. As the aeroplane moves through the air, it makes noise simply by disturbing the air. This noise emanates outwards in the form of pressure waves. These pressure waves stream out away from the aircraft at the speed of sound in all directions, acting just like the ripples through water when a stone is dropped in the middle of a still pond. However, as the aeroplane approaches the speed of sound, it actually starts catching up with its own pressure waves in front of it. These pressure waves turn into one big pressure shock wave, which causes a loud big bang, called a sonic boom. The shock wave generated actually buffets the aeroplane and decreases the lift force. Obviously, because of the increasing drag, decreasing lift, and aeroplane buffet, pilots need to know when they are approaching the speed of sound. Shown here is a picture of an aeroplane passing through the speed of sound. The shock wave actually causes condensation, which allows an observer to actually see the pressure wave. These two pictures show the shock waves on military aeroplanes flying at 3 times the speed of sound. The next scene will discuss a specific aeroplane's speed which allows pilots to know when they are approaching the speed of sound. On screen is the animated demonstration you saw earlier, but this time you can adjust the aeroplane's speed using the slider at the bottom. When you have finished, just click on the flashing forward arrow. The ratio of the speed of the aeroplane to the speed of sound in the air determines the magnitude and intensity of many of the effects of high-speed flight. Because of the importance of this speed ratio, aerodynamicists have given it a special name called the Mach number in honor of Ernst Mach, a late 19th century physicist who studied gas dynamics. Mach number is not an actual speed as such. It is, as we have already said, the ratio of the true speed of the aeroplane to the local speed of sound. Mach number is best illustrated using an example. To calculate the Mach number, simply divide the true airspeed by the local speed of sound. At sea level in icy conditions, the local speed of sound is 661 knots. If the true airspeed of the aeroplane is 510 knots, then using the formula on screen, the Mach number is 0.77. In other words, the aeroplane is travelling at about 3/4 of the speed of sound. If the aeroplane were to fly faster, the Mach number would increase. If the aeroplane accelerated to 661 knots, then its speed would be equal to the speed of sound and the aeroplane would be at Mach 1. Aeroplanes flying between about 0.8 Mach and 1.2 Mach are said to be in transonic flight. However, the term supersonic is more commonly known. Supersonic flight describes flight speed above Mach 1.2. The speed of sound varies with temperature. As altitude increases, the reducing temperature causes the local speed of sound to fall. At 30,000 feet, the speed of sound is 590 knots. If the true airspeed of the aeroplane is kept constant at 510 knots, as a result of the falling local speed of sound with altitude, the Mach number will increase. As the aeroplane's speed approaches Mach 1, the compressibility and approaching shock wave can have very detrimental effects on the aeroplane's performance if the aeroplane is not designed to mitigate such effects. As a result, most commercial aeroplanes in service today have a limit on the maximum Mach number they are allowed to fly at. This maximum operating Mach number is called MMO. The Mach number of an aeroplane can be displayed in a number of places in a typical cockpit. Shown here are just a few of these places. Having discussed all the relevant speeds of an aeroplane, it is important to understand the relationship of these speeds with one another as altitude changes. This is best illustrated on a graph. The y-axis is altitude and the x-axis is aeroplane speed. If calibrated airspeed, or simply indicated airspeed, is kept constant with altitude, then as density falls, the true airspeed will increase as shown. But if true airspeed increases with altitude, while the local speed of sound decreases, then the Mach number must increase. These lines representing these three speeds can be manipulated to help solve complex problems. If the true airspeed were to be kept constant with altitude, the TAS line would be drawn vertically and the CAS and Mach lines as shown. Now, calibrated airspeed decreases whilst Mach number increases. If Mach number were to be kept constant, the diagram could be drawn so that the Mach line is straight up. Notice that TAS and CAS decrease with altitude. The same can be done with decreasing altitude. If the CAS is kept constant during the descent, keep the CAS line vertical and notice that the TAS and Mach number lines slope as shown. This means that if CAS is constant during a descent, the TAS and Mach number will decrease. To help you remember how to draw the lines, C, T and M always appear from left to right. You can use Britain's favourite food, chicken tikka masala, as an acronym for remembering C, T and M.